Hello and welcome to Tonight at 8 from the RSGB. This is a little bit different to usual because I'm presenting and not just hosting this webinar. The BBC is probably best known to most people as a programme maker, informing through news and making content to educate and entertain. But as well as making the content, it's often been the pioneer and sometimes the developer of the technology used to make and deliver these programmes to the home, and it's this which I'll be exploring today. I should say that I'm neither an expert or historian on the BBC, but as someone who enjoyed working for them to make programmes several years ago, I was struck by how much of the equipment I used was conceived or developed by them, and so I felt that in this BBC centenary year we should take a closer look at the technology used by our national public service broadcaster. The presentation isn't deep or highly technical, and we can only look at a few of the key developments in the time that we have, but I've tried to make it interesting and accessible for everyone. If you are watching this on Monday the 5th of December, then this is live, and you're welcome to make comments, ask questions or share your experience either during or straight after the presentation using YouTube chat or BATC messaging. At the end of the presentation I'll also be recommending places to visit and links to some of the excellent resources which I've found during my research for this programme. And please note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So when you think of the different ways the BBC broadcasts, you probably think of sound in radio, vision, television, and digital services, well, originally text-based services like CEEFAX, but now a huge amount online with web services and other content supplied over the internet. Throughout this talk, I'll mainly be concentrating on the earlier technologies as these were the particular breakthroughs of their time. So where to begin? Well, the beginning. First, a little bit of history to bring some context to this period, as well as the relevance to radio amateurs. Before the BBC, most radio communications for everyday folk was by experimenters at home, often in the garden shed. Yes, radio amateurs. In fact, the RSGB predates the BBC by some 9 years, initially known as the London Wireless Club, but later becoming the Radio Society of Great Britain. According to Hansard, in February 1922, the Postmaster General had issued nearly 7,000 licences to radio amateurs for receiving, but only 286 amateurs had licences to transmit. At that time, the General Post Office, or GPO, issued all radio licences. Broadcasting was a very new and little used term, certainly in the UK, and although this presentation is about the BBC, I don't think it would be fair not to at least acknowledge at this point that the very first live public broadcast in Britain was not actually the BBC, but widely thought to be the Marconi Company from their headquarters in Chelmsford, using a 250-watt transmitter. Their station held the call sign 2MT, and although this was not the BBC, Marconi was still to have an important place at its launch. Back to the BBC. And the British Broadcasting Company was formed on the 18th of October 1922. Company because at that time it was a commercial organisation, as the government had brought together a group of electrical companies who had interests in communications, including Marconi, the General Electric Company and Metropolitan Vickers. The British Broadcasting Company based their first transmitting station in Marconi House in the Strand in London. It's thought one of the main reasons Marconi House was chosen was because a transmitter was already set up there. It was already transmitting in May 1922 with short daily test transmissions using a relatively low power transmitter like this one. This is similar to the one at Marconi's established broadcast site near Chelmsford. Initially, the 2LO licence issued by the GPO meant that it could only transmit for 7 minutes, but then had to listen for 3 minutes to check for interference with any official government communications. Marconi had started working on a much more powerful transmitter, and by the time the BBC was formed and located in Marconi House, they'd virtually finished this 1.5 kilowatt transmitter. The one you see here was donated to the Science Museum in London by Crown Castle and the BBC, and you can usually find it on display there. There's not too much written about the technical aspects of this transmitter, although it's believed that there were two top Marconi engineers, H.J. Round, who designed it, and C.S. Franklin, who made it work. According to BBC Engineering, H.J. Round in particular developed a lot of important technology, including pioneering the use of valves in high-power wireless telegraphy and telephony transmitters. In fact, Mr. Round averaged a new patent every 6 months, until his last one when he was 83. If you're interested in the intricacies of the design of this, I found a circuit diagram of this transmitter online recreated by Crown Castle, which you can find with a quick internet search. I believe the frequency first used was 857 kilohertz. That's about 350 meters. Now, this was the outside of Marconi House in the Strand, where first BBC radio transmissions started. There are actually much better pictures of the photos of the whole building, but this one shows some of the antenna on the roof of the Marconi building. You can just see there the wire antenna between the poles going between here and here. You could just make out either spacers or maybe junctions for feeders in the middle of the antenna as well around here. This is where the 2LO was transmitted from for the first years of the BBC, mainly to listeners in and around London. It stayed in service until 1925, when a transmitter, which was twice as powerful, took over, and that was based at the top of the Selfridges building in Oxford Street. The very first formal BBC radio programme was on the 14th of November 1922 at 6 p.m, opening with 2LO, 2LO, Marconi House, London calling, and was a news bulletin followed by a weather forecast, read by Arthur Burrows as seen here. He was also director of programmes. The content for his bulletin actually came from news agencies, as there was no BBC newsroom at that time. There's not actually very much written about the very early broadcasts, partly because the newspapers of the time did not tend to publish details of programmes because they were concerned about the threat that this new medium might pose to their papers, and the Radio Times is yet to be created. But it's known that it wasn't long before music and other entertainment were being broadcast alongside the news. In December of this year, a Scottish engineer by the name of John Reith was appointed as General Manager of the British Broadcasting Company, and he's largely credited for guiding the BBC through these early important years, even though he admitted he knew nothing whatsoever about broadcasting, but then nobody did at that time. Now, here I've only talked about this initial radio station based in London, but it clearly had a limited range, and so a range of other BBC radio stations were also set up across the country by other companies, such as station 2ZY in Manchester, run by Metropolitan Vickers. Initially there were a total of 8 stations based in London, Bournemouth, Birmingham, Cardiff, Manchester, Newcastle, Glasgow and Aberdeen. The BBC radio network was born. At midnight on New Year's Eve 1922, the BBC decided to broadcast the chimes of Big Ben. These were very early days. The BBC had only been on the air for just under 2 months. But hearing Big Ben was so popular that in February it was made a regular daily time signal. Now, of course, technically it wasn't too difficult to play the sounds of Big Ben, and in the early days they mounted standard microphones on the roof of the Palace of Westminster, but they also picked up traffic noise, etc. So later they used low sensitivity moving coil microphones like this one, which were located next to the bells and didn't pick up the sounds of traffic and other noise from outside Big Ben. What's this time stuff got to do with BBC technology? Well, the Big Ben transmission became so important to people that BBC boss John Reith plus Astronomer Royal Sir Frank Watson Dyson decided the BBC should broadcast a regular time signal for the nation to use. And so the Greenwich time signal was invented, then and now known as the PIPS. Originally, the master time signal for the BBC was created and sent by the Royal Greenwich Observatory, and the picture here shows some of that equipment. The RGO had 2 very accurate for the time mechanical clocks, which they modified so that the pendulum roller contact sent a signal down a dedicated telephone line to the BBC. And here's a circuit diagram of that. It may sound as if the system should be quite complex, but I found this circuit of the link between the Royal Greenwich Observatory and the BBC as it was in 1946. It was on a very interesting website called ORBEM, which stands for Old Radio Broadcasting Equipment and Memories. And it also, by the way, has other details of BBC installations including wartime studios and control rooms. This shows the relatively straightforward circuitry at the Royal Greenwich Observatory on the left, the telephone line in the middle, and the BBC apparatus on the right. The meters allow each location to check the continuity and quality of the connection, and was added after occasional problems with earlier systems where the BBC did not realise there was no Royal Greenwich Observatory signal until they went to use it. The GTS OSC box at the BBC end, which is just here, refers to the 1 kHz oscillator. As it does now, the system generated 6 1 kHz pips, with the final pip marking the first minute of the new hour. The system had various updates as technology in timekeeping and transmission advanced, including when the RGO moved from Greenwich to Hurstmonceux Castle. But in 1990, the Greenwich time signal transmitted its last pips to the BBC. Since then, the BBC has originated its own pips within Broadcasting House, based on signals from the GPS satellite network and from the accurate 60 kHz radio transmitter at Anthorn in Cumbria, whose time is originated from atomic clocks. Now, we talked about the network of relatively small BBC transmitter stations set up over the country, and although these did a reasonable job in their areas, the BBC was still a long way from being a national broadcaster. So plans were made to try and find a suitable site from which to broadcast to most of the country. And the site eventually chosen was on Borough Hill near Daventry, and it opened on 27th of July 1925. It had the call sign 5XX and was the world's first long-wave transmitter station, and it brought the audience within reception range to over 85% of the population, and made the idea of a nationwide radio service a reality, proving that using high-power transmitters was much better than using lots of smaller ones. These photos show parts of the transmitter hall, although the actual electronics that we now call transmitters were called senders. And this picture shows the outside of the Daventry site with a relatively modest number of masts and antenna. At its peak, there were over 40 masts covering various bands and taking up hundreds of acres. Although Daventry was essentially only a transmitter site, broadcasting audio from various studios, it also became a site for some programmes to be broadcast. This picture shows what is believed to be a World Service programme being made from the inside the transmitter hall for live broadcast on the Empire shortwave service, which was later became the BBC World Service. The Prime Minister of the time, Stanley Baldwin, sent a message which was published in the Radio Times. He said, "The opening of the wireless broadcasting station at Daventry will give no less than 20 million people the opportunity to receive both education and entertainment by means of cheap and simple apparatus. And I look upon Daventry as another milestone on the road to the social betterment of our people." Now this is what the Empire Service building at Borough Hill near Daventry looks like today, with the entrance to what was the transmitter hall. And this is the plaque outside the building marking its historic past. Most of the former BBC transmitter sites are now owned by Arqiva, and on the centenary of the BBC formation, 18th of October 2022 this year, Arqiva Amateur Radio Club hosted a special event station with the BBC Amateur Radio Group to commemorate the event, and my ex-YL Tammy M0TC and I were very pleased to be able to go along. As you can see, this transmitter hall doesn't look anything like it was, and is now used as a training and conference centre for Arqiva personnel. But for one day only, it became home for this special event, and this photo shows RSGB GB2RS news manager Steve Richards G4HPE at the microphone of special event call sign G2LO, alongside one of my friends and former colleagues from my early days at the BBC in Cambridge, Nick Garrett G0OQK. The station also operated as GB100 BBC, the BBC Amateur Radio Group's special event call sign, which is running throughout 2022 by its members to commemorate the centenary. Outside, all that's left to give a clue to its past are lots of concrete stands from the many masts that the site used to host here. But this picture also clearly shows the wonderful elevated and remote area on Borough Hill. That's quite a height for that generally flat area of the country. There's just one main mast left at Daventry now, and that hosts DAB coverage, and the rest of the site is used for Archiva maintenance and training. Before we leave Borough Hill, something which may appear rather random to include. These are rainwater gullies that I noticed around the transmitter hall and show early versions of different BBC logos or branding, alongside what was presumably their installation dates, 1932 and 1937. I thought it was interesting anyway. Back to the past. And although we have looked at the transmitters and antennas of the time, we haven't yet seen what listeners at home heard these early broadcasts on. This picture is of an early crystal set from the 1920s, which would probably have been made by one of the manufacturers making up the British Broadcasting Company, and which you can see is badged with the BBC logo. Note what it says around the main letters, type approved by Postmaster General. Although relatively simple and inexpensive, most of these types of sets only had one set of headphones for listening, so could only be heard by one family member at a time. Later, radios with loudspeakers, which the whole household could hear, would become available. Receiver designed by the McMichael Radio Company, which was very high-end. It was portable and designed rather like a picnic set, where once opened the lid turned into the loudspeaker housing. One of these was even presented to King George V. Now, I guess most of us would take a microphone for granted nowadays. But of course, in those early days of broadcasting, there was not a wide choice available. The American RCA company had developed a ribbon-type microphone for use in broadcasting and films in Hollywood. It was a very good, but cost over £130 in old money, which would be over £5,000 today. Excuse me. The BBC had already set up its own research and development department, and as it realised it was going to need a lot of microphones, it decided to develop its own in-house. And the result was this microphone, which was called the BBC Microphone Type A. The Orbem website has archived some impressive details of the Type A microphone and have kindly allowed me to share these with you. The BBC microphone was also a ribbon-type microphone and consists essentially of a thin corrugated ribbon of hard aluminium, approximately 2.5 inches long and 1/4 inch wide, and just 0.2 thou thick. Suspended in the gap formed by the specially shaped soft steel pole pieces of a large cobalt steel permanent magnet. Movement of the ribbon in response to the sound in a normal direction to its face gives rise to current along its length. The resistance of the ribbon is only about 0.15 ohms, and so a mu metal transformer, forming part of the microphone assembly, is incorporated in order to step up the output impedance to a more usable 300 ohms. The Orbem website shows in extraordinary detail how these microphones operate and the balance technique which the studio had to use to set each microphone up. This image is of an extract from the instructions which the BBC engineering department wrote for their microphone, showing its directional characteristics and advice on how and where to locate it for musical performances. Once developed, the BBC asked Marconi to manufacture the microphone for them in around 1935, and it came in at a cost of around £9, a lot less than £130 for the RCA model. It became the standard for many years of studio work, with several improvements being made, finally resulting in the Type AX-BT. And finally, a thought for you. Although you may think that these microphones look really old and couldn't possibly still be used today, think again, because there's a British company called Coles Electroacoustics Limited, based in Hertfordshire, which still actively manufactures and markets a range of microphones to professional broadcasters around the world, many of them based on original BBC designs, including this 4038 studio microphone and the 4104 commentator's microphone. Most of the radio broadcasting we've talked about so far has all been live, but of course there's also a need to be able to record, not least for practical convenience in time-shifting programmes and for posterity. The ability to record sound has been around a long time, since around the late 1800s, with Thomas Edison's phonograph one of the first commercially available, and is what you can see in this picture with the inventor. Edison's first models worked by indenting a sheet of tin foil into a groove on a cylinder, and later versions used wax cylinders on drums. But this was not a very practical way to record the audio from electronic microphones in studios, etc. In fact, the BBC had no viable means of recording its audio until around 1930. By the early 1900s, several inventors were experimenting with electronic audio recording using an electromagnetic head to record onto steel wire. But among the first practical and viable recording machines was the Blattner phone, designed by and named after German-born inventor and film producer Louis Blattner. His device used 6mm wide steel tape to record a very basic audio signal, which was good enough for voice, but not really good enough for music. The spools were large and heavy, and the high speed at which the machine ran, around 5 feet or around 1.5 meters per second, meant that it was hazardous for the operator, because a break in the tape could result in razor-edged steel flying around the studio. A full reel lasted about 20 minutes, and editing was done by cutting into and then soldering or spot welding the steel tape back together, which you could hear on playback, so hardly ideal. But it was practical to use in a broadcast environment, and the BBC adopted the Blattner phone as its first mainstream audio recorder. It was particularly useful for the BBC's Empire service, which became the World Service, as it enabled it to broadcast through the night to many countries without having to have presenters, reporters and artists, etc. performing live. But the Blattner phone had several shortcomings, including relatively short recording times, fluttering sound and safety concerns. So around 5 years later, this machine by Marconi Still was adopted by the BBC as its new generation of main recording machines. This used much narrower steel tape, and one of the ways that it provided better sound stability and lower flutter was by having a sort of buffer of tape in the central V-shaped area, so that the tape speed past the head was not only dependent on the constant take-up speed of the large reels as in the Blattner phone. You can just see that area here, and in there. But before you think that this picture looks almost like a conventional tape recorder, bear in mind it's very large and heavy, and is floor standing on its own legs. You can just see that in the bottom left of the picture there, and this weighed around about a ton. So far, the audio recorders we've seen have been developed by companies for use by the BBC and other broadcasters. But as we've seen already, sometimes the BBC finds there's nothing ideal for its purposes, and so its engineering department develops its own. And so it was with audio recording, because the BBC's engineering department also developed its own disc recorders. I found this picture and many other details about the BBC disc recording equipment Type D on the BBC Engineering website, where the full service and instruction manual was there and where this picture came from. Excuse me. The website is a wonderful collection and resource of many of the BBC engineering projects and products. The spec in the service manual says that the disc recording equipment Type D was designed by the BBC Research Department to meet the need and demand for a recorder with a high fidelity performance which would be thoroughly reliable in service and reasonably simple to operate. And this recorder worked by effectively making what we'd now call a record, a disc with grooves made by the special recording heads on the BBC Type D recorder. The instructions even say that it can make discs to run at 78 or 33 1/3 RPM, two of the standard record speeds of the time. Now first, I must admit that I thought it was rather odd making effectively a record maker when magnetic recording technology was clearly progressing well. But thinking about it more deeply, I realised that a disc was very much more portable, relatively low cost, probably quite robust as long as it was stored correctly, and a disc would enable instant access to replay parts of recordings without having to run through thousands of feet of steel tape. Now finally, a quick mention of portable recording. The BBC developed this midget disc recorder with the Marguerite Sound Studios company to be able to report directly from the front line of the Second World War. The recorder came with 12 10-inch discs, which had just under 3 minutes recording time on each side. and there's a light to warn the reporter when their time is nearly up. The discs themselves broke easily when they were cold, so in the winter reporters kept them inside their coats to keep them warm. It's incredible to think that this drive mechanism was powered by a clockwork motor, and it had 2 recording settings, one to limit background noise so that the reporter's voice could be heard, and another which played everything, including the sounds of the battle. Although this was designed as portable, it weighed around 18 kilograms and only 72 were made. I actually took this picture at the Science Museum in London, where it's in the BBC at 100 display cabinet. Now, although this talk is only in loose chronological order, we're now in January 1927, and the British Broadcasting Company has become the British Broadcasting Corporation by Royal Charter, with former General Manager John Reith becoming Director General and a Sir. With radio now becoming a part of everyday life in Britain, there were several people already working on the idea of transmitting pictures by radio and not just sound. As you can see from this small advert from the Times newspaper in 1923, one of these people was John Logie Baird, who asks for someone to help him make a working model to prove his ideas. The advert reads, "Seeing by wireless, inventor of apparatus wishes to hear from someone who will assist, brackets not financially. Write to Box S, 686 The Times EC4. Well, the basic idea of television as we know it today is similar even to those early days, although the method of achieving it is very different. To try and put some context into the period without drowning in a sea of dates, radio was becoming established, and there were already early facsimile machines capable of sending still images over telephone lines to a remote printing machine in the late 1800s. Back to television, and for those of you watching who are not sure, let's just quickly go over how a basic television picture is made. This only describes black and white because colour wasn't to appear for many years and is much more complex. So let's start with a simple image which we want to televise, like this cross. My simple interpretation of a television picture is that you need to scan the image you want to convert into an electrical form by breaking it down into very small parts and then taking a measurement of the brightness of that part and sending that electronically along with all the other small parts which make up the total picture to some other electrical device capable of recreating and displaying that picture. It's important to bear in mind that the whole TV picture is not all sent at once, but sent in smaller parts sequentially. So in this digital age, we would break the image down into smaller areas like this, now called pixels, to define and then transmit the picture to a compatible display device to recreate the image on a screen. But back in the 1920s, this wasn't easy to do, and it's the technology that's used to scan and break the image down into smaller parts which were in stark contrast to each other for the pioneers of early television for the BBC. So now let's have a look at the 2 different methods the BBC had to consider. Probably the first and most well-known television system was proposed by John Logie Baird, a Scottish inventor who incidentally, although is probably best known for his work on television, backed most of his pioneering television research with money he'd made from one of his first commercial inventions, the Baird undersock. But Baird had been interested in telephone systems and the like from a very young age and had studied several patents of other inventors who had various ideas for sending pictures over wires or radio. But it was actually a patent by Berlin inventor Paul Nipkow which interested him greatly, and you can see it here. The patent was titled the Electric Telescope and described a system where the image scanning was done by a mechanically rotating disc, which came to be known as the Nipkow disc. As the patent will probably not be very clear to you at home, I've redrawn the disc to hopefully show the principle of the Nipkow disc more clearly. And you can see that you've got a spiral of holes going round the disc, getting closer to the middle as it goes round. If I now superimpose the image of the cross that we saw earlier, hopefully you'll get more of an idea of how it worked. The basic principle is that this disc rotates and projects or scans a very bright light onto various parts of the subject you want to televise. The amount of light reflected off the subject as the disc rotates will be proportional to how light or dark that part of the subject is. This reflected light is picked up by a selenium cell, which was one of the earliest forms of photocell at the time, and that generates a small amount of electricity which is proportionate to the amount of light shone on it. The receiver, which Baird called a televisor, works in reverse with a similar rotating Nipkoff disc with a matching spiral of holes and a lamp behind whose brightness is in proportion to the signal level from the selenium cell in the camera, so reproducing the image of the subject. John Logie Baird was to use his version of the Nipkoff disc at the heart of all of his early television work. And this is one of John Logie Baird's actual patents from January 1929. It was titled Apparatus for Transmitting Views or Images to a Distance. Like most patent applications, you want your patent to be as non-specific or wide as possible so that others cannot easily get around it. So you can see here, there's the Nipkoff disc. It starts actually with this, which is called radiation from generator on his patent. I guess that's the very strong light source, maybe even a spark gap looking at that. And the lens, there's the image that you're trying to televise, the Nipkoff disc. Goes into 12, which was a suitable detecting device. 14 was an amplifier. And then below you can see the receiver, where the output was fed into another receiver, an amplifier, and that was a lamp, a visible light, which shone through the Nipkoff disc in the receiver, and then you could see the image that was being transmitted from the camera there. So this is one of Baird's original experimental television apparatus from around 1925. You can clearly see the Nipkoff disc, which was actually two sets of spiralling holes with lenses in. From my research, I believe this was so that the disc only had to spin half the speed because it would have two sets of scans per revolution, although later discs had 30 or more holes for a better resolution picture. In many of the pictures which exist of Baird's work, it shows he used a ventriloquist dummy head for the image, like this one. This dummy was actually called Stokey Bill. This was partly because he often worked alone, but also because he had to use very bright light sources to try and achieve good contrast using the rather basic selenium cells of the time. And these conditions would have been very, very hot and difficult for a real person to bear for long periods. The ventriloquist dummy's mouth would have been able to be moved as well, so that it could be seen this was capable of moving live motion television. One of the biggest problems that Baird faced was to get a good range of shades of grey with enough details to make out features. So he tried using bigger discs with more powerful lenses. But there are accounts of discs coming off and flying around the lab, shattering lenses as they went. Now, this original equipment is in the Science Museum in London and the Science and Media Museum in Bradford and is well worth visiting to see in the flesh. Now, this is a short clip of John Logie Baird's early experiments, which I've been granted permission to show you by the BBC. Well, one of Baird's major breakthroughs came when he could display better resolution and shades. And in January 1926, he gave us what's thought to be the world's first public display of television to the public inside Selfridge's department store in Oxford Street in London. This is one design of television receiver for the Baird system to be used in the home, called the Baird televisor. Distinctive in this model, with its shaped cover over the disc, note how relatively small the viewing window was. You can just see that here. Very small. This original equipment can also be found in the Science Museum as well, so well worth visiting to see in the flesh. The BBC were getting interested, but whilst showing his invention to an intrigued public, there was another television system being developed by rivals not far away. One of the most distinctive aspects of Baird's early television work was that much of it was mechanical, requiring motors, gearboxes and other mechanical parts to operate. But then, of course, at this point in time, most electronics was far from solid state in the way we think of it now, with thermionic valves, or tubes as they're known in some parts of the world, invented in the late 1800s and at the heart of amplifiers, oscillators and other active circuits. Engineers were discovering that the effect of cathode rays could also be seen if an electron gun mounted inside a valve is aimed at a phosphor screen and could be deflected either electrostatically from plates around the beam or creating electromagnetic fields using coils. Called the cathode ray tube, this photograph is of the Braun cathode ray tube, named after the German physicist Ferdinand Braun, who most people seem to accept was the first person to realise that a CRT could be a display device. So the cathode ray tube is starting to be employed as a display in test equipment, such as the oscilloscope here, to show waveforms in electronic circuits. And so in theory it should be possible to make it show images for what we now know as television. So lots of inventors and engineers around the world were trying to figure out ways of capturing the image. But it was actually another Scottish engineer called Alan Campbell Swinton who really had the vision that the CRT could be used as the basis of electronic television. Well, this talks mainly about the technology developed, commissioned or used by the BBC. So I'll only show now the one other system which the BBC effectively shortlisted for television comparison and trials. But bear in mind that there were many other engineers and businesses working around the world who could see the possibilities and were all working on television by this time. This is from the patent of the Emitron camera tube, which engineers William Dedham and James McGee were working on at Electrical and Musical Industries, or EMI. The patent was granted in 1934. You can see some clear physical similarities to the cathode ray tube, with the electron gun at an angle. In very simple terms, the Emitron camera tube works like this. The subject to be televised, I've shown here as a cross, is focused by a lens to create an image on the photosensitive mica screen inside the tube here. Gradually it scans it from side to side and top to bottom using electromagnetic fields created by coils. The output from the mica screen varies with the brightness of the image as it is being scanned, and this signal is amplified, ready to send to a television receiver. And this is a photo of an actual Emitron camera tube at the Science Museum. Although it may seem apparently simpler to explain than the rival Baird mechanical system, it required much more sophisticated electronic circuitry for all of the high voltages, scanning and amplification, etc. But it was relatively speaking more compact and solid state, so making it possible to fit into a mobile cabinet like this. And so this is what one of the first Emitron camera tube based cameras looked like. You can see the distinctive nose of the camera here, which was used to house the long neck of the Emitron camera tube. And this is what it looks like inside, with this open-sided view of the camera. You could just about make out the tube going along the bottom, lower edge of the slope there, in there. You may have noticed that there are two lenses on the camera. Well, on the original prototypes there was no viewfinder where the camera operator could see exactly what they were televising. So on later models another identical lens was fitted so they could see what the camera was seeing. Although because of the way optics work, the image they saw through the adjacent lens was probably upside down, but it would still enable them to frame a shot. Finally, for completeness, this is a picture of a typical television of the time to receive pictures of the Emitron system. This is called a Marconi phone 701, which shows that television receivers based on cathode ray tubes were usually relatively bulky and complex compared to a Baird televisor. The cathode ray tube was often mounted vertically, with its screen viewed on a mirror mounted at 45 degrees in a tilting lid. So there we have a brief overview of two completely different systems for delivering television pictures. the John Logie Baird system, with images scanned and reproduced by a relatively simple rotating disc of spiralling holes, and the more compact but more complex Emitron system of all electronic scanning. Technically, they were very different systems, and both clearly wanted to become the standard for television broadcasting. So somehow a decision had to be made on which system to adopt. The BBC engineering department had been working and closely watching with both companies, Baird being the smaller company, but had been working on the technology for a long time, and in some ways much bolder in its approach to showing the public what television was all about, and EMI coming to the technology later, but with fresh ideas and joining forces with radio transmitter pioneers Marconi to form a formidable contender. Although it would be the BBC who would become the broadcaster of this new public service called television, the government decided that the decision on which system should be adopted should not just be made by them, so they appointed Lord William Selsdon to set up a television committee to consider the development of television and advise the Postmaster General on the relative merits of several systems and on the conditions under which any public service of television should be provided. This wasn't going to be easy, as the BBC was already working closely with Baird, transmitting almost daily experimental broadcasts of entertainment as well as news from purpose-built studios at Broadcasting House. Baird had overcome one of its most serious problems of needing very bright lights and high levels of makeup on artists to get sufficient contrast by a lateral thinking but cumbersome method of literally filming using traditional celluloid film cameras, then immediately processing it and scanning it using the earliest form of flying spot scanner, effectively televising the film. This process was done in just under a minute, so not quite live, but probably live enough for most programmes. By the time of the trials, the Baird system had reached over 200 lines resolution instead of the early 30 lines, but Marconi EMI had 405 lines. Well, the BBC produced a really good short video to show the trials of these competing systems, which includes special archive footage, and they've given me permission to show you this here.
In 1925, inventor John Logie Baird transmitted an image of a puppet called Stooky Bill. It travelled only a short distance and was hopelessly poor quality by today's standards, but it was the beginning of television. Baird's company quickly took off. By 1932, they could transmit pictures down 400 miles of telephone cable between London and Glasgow. But they were still using wires. What Baird really wanted to do was broadcast over the airwaves. To do that, he needed a transmitter, which meant working with the BBC. Dr. Cassie Newland has been to where it all began.
All inventions, if they are to change our lives, need to find supporters beyond the workshop. For television, that meant attracting an audience. In 1932, Baird began test transmissions from Broadcasting House, but he soon had competition from a rival system, electronic television, led by the powerful corporation EMI. The government had to select the best invention.
They asked the BBC to conduct an extraordinary experiment in which mechanical and electronic television would compete head-to-head. And this is the site of the battle, Alexandra Palace in North London, which in November 1936 would play host to the world's first television talent contest.
A former Victorian entertainment venue, the site had the height and range for the transmitter and space for 2 separate studios. Baird Television Limited's mechanical system was given Studio B, while in Studio A were the newcomers, now called Marconi EMI. Their system employed electronic technology, which had been proposed by Scottish scientist A. Campbell Swinton in 1908, based on the recently invented cathode ray tube.
76 years ago, this studio would have been full of the people and equipment of the Marconi EMI team. Both teams were given 6 months to prove themselves. At the end of the contest, the best system would be awarded the coveted contract to broadcast to the nation. The loser would go home with nothing.
transmission started on the 2nd of November 1936. The opening ceremony was broadcast twice, first with the Baird cameras and then again on the Marconi EMI system. To the viewer at home, the picture quality was evenly matched, but Baird knew he had a battle on his hands.
The mechanical systems that Baird was using had been refined over 10, 12 years and really had got as far as they could possibly go, whereas the EMI electronic system was still in its infancy.
Despite this, EMI's Emitron camera showcased the latest advances in electronics. The camera pointed towards the host and the picture focused onto a light-sensitive plate inside a cathode ray tube. The plate was then scanned using a beam of electrons, which was directed in lines across the image by electromagnets. This produced a series of electrical signals which were sent to a transmitter. The brighter the area on the picture, the stronger the signal. At the other end, another cathode ray tube converted the signal back into an electron stream. This was directed in parallel lines onto a fluorescent TV screen, and the successive scans built up as a picture.
EMI had 3 cameras in the studio, and you could take a picture from any one of the 3 cameras. You could put the camera on wheels, it was relatively light, and you could wheel it around the studio. It was television as we understand it today.
Under pressure to match the quality of this slick new system, Baird devised an incredibly complicated technology based on celluloid.
They filmed what happened in the studio on film. The film came straight out of the bottom of the camera into developer, into fixer, and then into water, and while still wet and underwater, about 54 seconds later, it was scanned to produce a television picture.
Baird's system, while offering good picture quality, was flawed. The cameras couldn't move, the developing process required dangerous chemicals, and it wasn't live.
It soon became clear that Baird's mechanical system had reached the end of the road, whereas for electronic television, it was just the beginning. Marconi EMI offered superior performance and were improving every day. As one of the producers said, it was like using Morse code in one room when you knew next door you could telephone.
It is in the nature of invention that first is not always best. The incremental improvements and adaptations of rival systems can take an invention further than the original inventor ever could. After 3 months, Marconi EMI was declared the winner. Baird had lost out.
In defence of Baird, to say that his system failed is rather like saying that Trevithick's first steam locomotive in the streets of Cornwall failed, and therefore he has nothing to do with the history of the motorised vehicle. If you go back to the beginning of any invention, it bears no resemblance to the state it's now in. But that shouldn't really detract from the fact that he was the person who proved to everyone that it could be done.
Thanks to the BBC again for allowing me to play that as part of my presentation. Such a wonderful array of unique footage they did. I hope that explains the story of television. Well, I have to say that from all my research, I feel that it sums up fairly why the Emitron system was adopted, but pays due credit to John Logie Baird for his pioneering work on television and his determination and ingenuity to overcome problems. Baird went on to continue to work on television, including colour and even 3D television. So if this has stoked your interest in his work, I can thoroughly recommend this book. It's called The 3 Dimensions of John Logie Baird, written by Douglas Brown, GM8 FFH, and published by and available from the RSGB. So the Emitron technology, with its relatively high 405 lines of resolution, became the backbone of the BBC, and later other British broadcasters' television systems, right until the 1970s, when 625 lines and colour came in. But that's another story for another day. Just as the facility to record audio is important for radio, the ability to record television pictures, or video as it had become known, was equally important. As one of his many inventions, John Logie Baird had proved he could record his Nipkoff disc camera pictures onto shellac discs, rather like records, which he called phonovision. But this system would not work for the higher resolution video of the 405 line system. Although a seemingly obvious way to record television was to use traditional cine-film camera, in practice this was much more difficult, as you need to synchronize the movie film frames with the television frames in order to avoid unwanted bars and distortion. But eventually, television recording as it became known, was made a possibility using electronics to synchronize the film and television frames, and this was how the early television recordings of important events were made, most notably recording the coronation of Princess Elizabeth II in 1953, where over 20 million people in Britain watched it on television. Of course, there are no broadcast satellites then, but according to my research, reels of freshly tele-recorded films were flown to countries of the Commonwealth like Canada in specially modified planes with film processing on board so that the films could be shown as soon as the plane arrived in the country. But tele-recording was relatively expensive because of the single-use film stock and time-consuming because of processing the film. So electronic methods of recording video were being researched by various organisations around the world, including the BBC. And this was the BBC's answer. It was called VERA, which stands for Vision Electronic Recording Apparatus. It was a project developed by BBC Research, an engineering department led by Peter Axon, and was started in 1952, although it took 4 years to get just to a working demonstration stage and another 2 years before it was ready for service. It had several advantages over tele-recording with film, as it only needed to be rewound before replaying, and as the magnetic tape could be reused, it had much reduced running costs. However, the 20-inch reels still only gave 15 minutes recording time, as the half-inch tape was travelling at over 200 inches per second. But it was a real achievement. However, by the time the project was being trialled, an American company called Ampex was showing their machine, which had a number of advantages, not least a much slower tape speed because of their quadruplex recording system. Sadly for VERA and its dedicated development team at the BBC, the advantages of the Ampex system soon became obvious, and this VR1000 became the world's first commercially manufactured video recorder and was adopted by most world broadcasters, including the BBC. Although the tape was wider at 2 inches, it ran at a much slower rate of around 15 inches a second by using 4 rotating heads which recorded across the tape, thereby effectively increasing the bandwidth of recording capability and so the length of recording time per reel. It's also worth noting that the rotating heads technique was to become the basis of all videotape recorders in the future. Although this photo makes the VR1000 video recorder look smaller than the BBC's VERA, there were several other cabinets of electronics needed to use with it, and the BBC had to get their first samples modified to work with the British 405 line television standard. Videotape recording, or VT, became an essential for all broadcasters, and eventually viewers' homes, and although there were massive improvements in quality, performance and usability with the use of cassettes, it's only relatively recently that videotaping has been replaced by hard drive and solid-state memory recordings of video. And the VT name, of course, still lives on with many broadcasters. Well, from television back to radio, which is also progressing. Coverage is now nationwide with many more stations on the air, and sound quality was greatly improving with FM being introduced in the 50s. Digital electronics was also starting to appear in more and more everyday products during the 70s, things like pocket calculators and digital watches with LED displays. The European Broadcast Union, or EBU, is a group of public service broadcasters who work together to facilitate joint productions, like the Eurovision Song Contest, and create and innovate technical facility standards between broadcasters in Europe. It identified benefits of being able to include basic digital data with analog radio to enable simple messages to be displayed on the radio receiver to show how it worked. So, for example, a radio could display the name of the radio station it was tuned to, show the precise time, or display weather messages. The system developed was called Radio Data System, or RDS, and the BBC saw great possibilities, and its development teams took a strong role in the development. The EBU published agreed technical standards in 1984. However, to ensure its success, not only would broadcasters have to build the equipment and infrastructure to add RDS data to their transmissions, but crucially persuade radio manufacturers to make radios which included RDS capabilities. The idea was to send the data by adding a subcarrier to standard FM frequencies, which would be inaudible to listeners and decoded by suitable electronics in the radio receiver. This is a scan from the information brochure published by the BBC to publicise the forthcoming service to the public and encourage manufacturers to adopt it. And you can see there in the bottom there is the waveform and the critical RDS subcarrier just at the end of that block. The EBU felt that motorists would benefit most from the system. So, for example, the RDS system could bring important news flashes, display local traffic conditions, and even auto-tune the radio to stronger frequency as the driver moves around the country. The first services the BBC transmitted were the station name display, accurate time and date, auto-tuning, and the RDS travel service, which you could turn on to allow the system to automatically interrupt any other station you were listening to bring you the travel bulletin from local BBC radio station in your area, before switching back to whatever you were listening to before. So early marketing was targeted at car radio manufacturers, and of course the chip makers who would make the technology sure that it was easy to incorporate into the radios. But it was to take some years into the 90s before it became commonplace, until most FM car radios came with RDS as standard. This page of the BBC brochure shows some of the other ideas for the RDS system, some of which appeared and some of which never made it, probably because digital audio broadcasting, or DAB, was coming along the tracks, and being all digital made it easier to embed non-audio content data. Well, television was also moving on, and by the 1960s most people were enjoying higher resolution 625 line pictures on UHF. In July 1967, the BBC pioneered the first regular colour TV broadcasts in Europe on its relatively new BBC Two channel. Although colour television sets were initially relatively expensive and unreliable, so most people tended to rent them. But as well as watching video programmes on television, engineers had ideas for another service which could be delivered into the home via the television, and it was called teletext. Now, frankly, from my rabbit warrens of research, it's a little unclear who actually invented teletext, because I've seen papers written by engineers at Philips and other companies, as well as patent applications by BBC research staff. But what is certain is that all these smart people had worked out ways that digital data could be encoded into some usually unseen spare television lines of a television broadcast, so that it should be possible to send data and build up text displays of information. Eventually, as it had to be, a standard was agreed so that the key players in the electronics industry, including Philips and Mullard, and broadcasters could work together and make a teletext reality. This television is an early prototype of an adapted television made by the GEC company, with all of the teletext decoder electronics in the large extra wooden box underneath. The BBC's teletext system was called CEEFAX and was launched in 1974, and they were the first broadcaster in the world to adopt and launched a teletext service. The system was not interactive, and so once you'd selected the page number you wanted, you had to wait for that page to be transmitted, as they were all sent sequentially. However, frequently requested pages like the index and news were regularly sent, so that there was not such a long wait for these. Of course, it wasn't just about the technology, but all the people resources needed to support such a service, creating pages of news, sport, weather around the clock. Although you could buy standalone teletext decoders, they were expensive because, as well as containing the electronics to decode, select and store the pages of information, they also needed to have their own television tuner to receive the signal and extract the teletext data. But eventually, televisions with teletext built in became reality and available to the public. And Mullard, one of the main chip divisions of Philips, produced a teletext chipset which became virtually the industry standard for many years. A few years later, ITV launched their equivalent service, which was called Oracle, and used the same technical standards so that existing TVs were fully compatible. Incidentally, I was very excited by the prospect of teletext myself, and can personally vouch for the fact that the discrete electronics needed to decode teletext was significant at the time, because I attempted to make a decoder from a long series of articles in the television magazine at the time. It consisted of 4 home-etched circuit boards full of discrete chips, mainly TTL logic and memory chips, and sadly I have to admit I never got it to work fully. CEEFAX served viewers well for some, giving them the first taste of CEEFAX served viewers well, for some giving them the first taste of computer-type displays in their homes. In fact, the 1980s, the BBC launched a subscription service called Datacast to deliver programmes and data for home computers, including their BBC Micro, which even included a Mullard teletext decoder built in. The BBC, CEEFAX and similar services ceased when the last analogue television transmitters were switched off in 2012. But the concept of delivering pages of information alongside television pictures and television programmes lives on, using services like the red button services on Freeview and of course the website. But if you missed the slow but sure CEEFAX service, there is an answer, because a smart 20-year-old called Nathan Dane has authentically recreated much of the CEEFAX service in every way, including up-to-date news and weather, on his own internet website. And I'll give you the link for that at the end of this webinar. So far, we've seen how the BBC embraced and sometimes helped to create evolving technology in broadcasting, first in radio and then television. And then by the 1980s, it was clear we were entering a new technological era, the age of computing. Since the main aim of the British Broadcasting Corporation was to inform, entertain and educate, both the BBC and the government felt there was a need to really support this new age with a strong campaign, and so the BBC Computer Literacy Project was born. The project was started in 1979 and launched in 1982 and was very ambitious, because not only was it going to help teach the children of the time through traditional television programmes in schools, but also educate and encourage the general public to understand and embrace the microchip and even use it in their own homes. The BBC's Education Division headed up the project, which started with fairly traditional television programmes about computing and how it was, or was about to, affect everyday lives. By the early 1980s, home computers were starting to catch on, with UK computer companies leading the world in many respects with relatively low-cost models. So it's probably unfair to say that initially many of these just got used to play games on. Initially, the buyers were mainly the electronics enthusiasts of the time, no doubt including radio amateurs, sometimes saving money by assembling them from kits. Now at this point, I'd love nothing more than to go into the ins and outs of the home computer industry of the 80s, as having served an apprenticeship with Pi, I was based in Cambridge at this time, and working Saturdays in the Cambridge computer store at the heart of these exciting times. But the home computer story is very well documented elsewhere, and I need to keep this talk on subject. The relevance to the BBC was that the team who were heading up the Computer Literacy Project soon realised that it needed to base the TV programmes and the extensive support materials on a specific computer, as although most of the home computers of the time used the basic programming language, this varied greatly between models, and besides, the BBC had ambitious plans of doing much more than just program computers. So with the Department of Trade and Industry backing, the BBC laid out the spec for what was to become a computer bearing its own name, and legend has it that through DTI connections started working with a Newbury-based company called Grundy, who were already developing a computer called the New Brain. However, other computer manufacturers, most noticeably Acorn and Sinclair, got to hear of this and made it clear that they also wanted a chance to bid for the opportunity to make the BBC computer, as they were already progressing with their next generations of computers of their own. Back to the BBC. and they urgently needed their computer to accompany the computer literacy project. And with quite an ambitious spec for the time, they awarded the project to Acorn. Fortunately, Acorn had already been working on their next generation Proton computer to follow the Atom, and they were able to adapt their design to meet the BBC's ambitious specifications. Now this shows the inside of an early BBC Micro Model A. The Model A had half the memory and not as many interface connections as the Model B, but cost £100 less, initially retailing at £235, so much more affordable for home users. But both models had a full-size proper keyboard and colour as standard, and a Model A could be upgraded to a Model B, and other upgrades like extra memory, hard disk drive interface, speech and networking could also be added. Schools were encouraged to buy the Model B and were given 50% of the cost towards it by government grant. And a lot of future-proofing had been built in as well, because within a few years you could buy add-on second processors, Prestel modems and even a teletext decoder to enable it to download BBC software direct from special CEEFAX pages. Every BBC computer came with a very good user handbook, explaining the basic interpreter and touching on the interfaces and expandability, plus resources like this computer book showing how a computer could be useful in the home. And of course, there was a plethora of software available for both games and more serious applications. And of course the television series, which were the backbone of the whole project, with the computer program at the core. Making the most of the Micro, which also had 10 episodes, and Computers in Control, which showed you how you could use your Micro to measure and control things in your life. In fact, I was fortunate to have several of my own products I designed and made in my Cambridge bedsit featured on that series. This was all on the back of the home computer boom, which one could argue would have happened anyway, but the BBC Literacy Project meant that everyday folk were now able to do much more than just play games on their computers. And although Sinclair's rival Micro, the ZX Spectrum, was around half the price, the BBC Micro sold in incredible numbers, with Acorn reputedly expecting to sell around 12,000, but in 5 years had sold over 1 million of them, including significant exports to the USA. Such was the demand for a well thought out computer backed by a huge amount of teaching resources and the BBC name on it. So that was the story of the Computer Literacy Project and the BBC Micro. I think most would agree that the project was a great success, educating so many people of the 1980s, old and young, to make best use of microcomputers and encourage future generations to embrace the Micro. But there is more. For whilst computers are now built into everyday products and are literally all around us, around 10 years ago it was realised that the UK faced a serious skills shortage in the technology sector. Boosting that skill set starts with educating the engineers of tomorrow. So BBC Learning set about working with 28 other partners on its most ambitious project since the Computer Literacy Project to launch the BBC Microbit. BBC Microbit is a small, complete microcomputer board which has a built-in matrix of LEDs, sensors and wireless technology, plus crucially loads and loads of resources to support its use, including coding and hardware connectivity. And such was the importance of the project that in 2016 schools could register on the Microbit programme to get a free Microbit for every 11 and 12-year-old student in the country. The Microbit's now on its second generation with built-in speaker, microphone and touch centre, and is on general sale for anyone to buy at around £15. And the BBC is still the overall editorial and project lead for the Microbit, coordinating the partnership, Microbit development and delivery, learning resources and on-air and online inspiration for teachers, schools and makers across the UK. The BBC and most other broadcasters seem to be positively thriving in this digital world. Look back 25 years to the late 90s and the radio and television programmes which started it all are still there, but many were now being created, edited and transmitted in digital form on services such as digital audio broadcasting on radio or Freeview and FreeSat on television, with the red button enabling interaction and much more information. Not only does digital broadcasting enable higher quality and extra services because it encodes and compresses the original signal, it takes up much less space on the spectrum, enabling many more channels to be fitted in the same space. For context, it's worth bearing in mind that at least in the late 1990s, mobile phones did not have built-in cameras, and in fact smartphones as we know them were at least 5 or 6 years away. The bbc.co.uk website was first launched in 1997 and looked a bit like this. It was pretty basic by today's standards, with mainly some news, weather, world service and programme listings, but then that was 25 years ago. There was also a feature called the BBC Networking Club, which was seen as an opportunity to build on the success of the BBC Microcomputer Literacy Project in the 1980s. The Networking Club was set up to accompany technology programmes such as BBC Two's The Net and Five Live's Big Byte, and consisted of a BBC-branded internet service provider, a website and the Auntie bulletin board. It was a relatively low-key part of the BBC's web presence, but encouraged feedback and ideas from people interested in technology, even offering its own internet access and associated services. Some of the BBC engineering and development departments were starting to move their attention from their traditional base of developing hardware equipment to the software challenges of offering an excellent online presence with innovative navigation, multimedia players. Indeed, it's hard for me to show the modern digital developments in the same way as earlier innovations because they're mostly clever software running on fast computers. But we got a taste of catch-up technology in 2001 with the launch of the BBC Radio Player, which allowed you to play live or play again some of the BBC's most recent radio programmes, as long as you had a good enough internet connection and a computer. It was quite different to do at the time, and whilst the technical challenges were formidable, the political and administrative barriers were even greater within the BBC and their programme makers, as it appeared to make some content available indefinitely to a huge audience. Of course, the BBC Radio Player was the forerunner to the iPlayer. That was launched in 2007, and that allows people to watch or listen to television and radio programmes live or from the past. And iPlayer is not only accessed by computer via the website, but accessible by apps built into televisions, phones and tablets. As we all get used to and watching broadcasts on demand whenever we want to, who knows whether there'll even be any scheduled programmes in 10 years' time. So what for the next 100 years of broadcasting? Well, of course, I'm not privy to what the next developments are, but I've looked at a few interviews and papers by people who work for the BBC and other media, and it seems clear to me that it will continue to become more and more internet-based. And since the internet is a two-way medium, probably radio and television programmes, if that's what they're still called, will be much more interactive. Well, you can get at least an idea of some of the things the BBC are working on from this website, bbc.co.uk/rd/projects. Please give it a look. Well, I hope you've enjoyed this brief look at some of the technology used by the BBC over the last 100 years. If you've not already done so, feel free to share your comments, questions and experiences of your own via YouTube chat or BATC messaging. Please include your name and your call sign if you have one in every message. And before we go to your messages, I'd just like to add that although I had some general knowledge of some of these subjects from my long-term interest, in researching this presentation I learned a lot more from books, online and visits, and I thought I'd share some of them with you. This video is of a visit we made last week to the Science Museum in London. Although their BBC 100 display is just one display case, there are many relevant displays of early radio, including this, which is the 1.5 kilowatt transmitter which was based at the Strand, Marconi House if you remember from earlier. And there's many other displays of other broadcasting and amateur radio equipment as well. This is some of the televisor equipment from Baird and Emitron. And these are some of the first amateur radio receivers and transmitters. So, to find out more, these are some of the places that I suggest you could go to. There's a Science Museum, as I just mentioned. That's some of the video that you've just seen. It's based there. There's the website. You may not have heard of the Science and Media Museum in Bradford. That's part of the same group, and that's their website there. But they've got a special Broadcast 100 special event there until 11th of January 2023. Well worth a visit if you're interested in broadcast and other sorts of technology to do with television and radio. If you're interested in the home computers and computing in general, the National Museum of Computing in Milton Keynes, they're just next to Bletchley Park and the RSGB National Radio Centre. Well worth a visit. And then the Centre for Computing History in Cambridge, which is a real wonderful step back to those 80s computers with many of them on display, and you can use them. Books as well. I used several books in researching this. These three are the main ones that I used. Radio Broadcasting by Gordon Braithwaite, available from the RSGB shop, as well as that 3 Dimensions of John Logie Baird. If you're interested in the person, this is an excellent book. It costs about £8. That's all from rsgb.org.uk as well. And then Broadcasting Britain, 100 Years of the BBC, which is a good general book about the 100 years centenary of the BBC, and that's available from most general book shops. And I think I missed by accident there one slide. Find out more online. Now there's lots and lots available online. I'm sure you will use the internet to search for things, but those in particular I recommend. Some less likely to find, like orbem.co.uk. The Narrow Bandwidth Television Org, nbtv.org, is a club that you can join to find out about making your own television equipment. I realise you won't be able to write these all down, but you can obviously watch this again and take a note of them later, and we'll try and get them put on the RSGB website as well. So thank you very much for watching. Thanks also to the executive producer of BBC 100 for permission to use the images and video that I've used. I could not have done this presentation without that. And also all the other organisations and websites have also allowed me to use material from their resources for this talk. The BBC Amateur Radio Group for the Daventry Special Events Station, and a really good contact for BBC 100, which enabled me to get that permission that I needed to show the images. To Tammy M0TC for her support while I was working on this presentation for rather longer than I thought. And the RSGB, of course, for giving me the opportunity. I'm going to take a quick drink there, and then I'm going to look at some of the questions or comments and things that I hope you've sent to me. I haven't had a chance, obviously, to read them because this is live. Where do I start, Tammy, on some of these here? Bev Marks says the travel service described was developed by the BBC in advance of other broadcasters using a new feature, Eon. So we helped all broadcasters via the EBU. Yes, thanks, Bev. I mean, this is, I think, some of the point really. The BBC haven't created all of these things, but I think they had the foresight to at least imagine and the imagination to come up with some of these technologies, which were often adapted and produced by partners that they worked with. Simon Hammond, he says, I used to have a teletext decoder on my BBC Model B computer. The BBC used to send software through it for users to download once a week. Exactly. Amazing way. I didn't know that at the time when CEEFAX was still a thing, but you could buy this adapter to plug into a BBC Micro. Thanks for that, Simon. Martin Ellis, don't forget NICAM sound. I realised there are several things I had to miss, including NICAM, which the BBC were at the forefront of development. There were so many things over 100 years that in just over an hour I just couldn't possibly cover them all. But as I said, some of those books and resources that I've linked you to, I think will enable you to find out more about some of those things. So I'm sorry for anything I missed that you particularly wanted me to cover. The BBC Micro, there's a lot of people remembering the BBC Micro fondly. And someone else says about their uncle helped develop NICAM, and he worked for Texas Instruments. This is such a big subject, I was quite surprised RDS had a mention. And NICAM was an important development. Yeah, I fully accept that. Let me have a look. What else have we got to cover here? My particular interest, this is from Paul G4DCV, my particular interest is in BBC loudspeaker design, especially the small LS3 5A monitor. My late father, G7URP, was on the design department team. And it was one of those things, Paul, as well, that I remember when I worked in a radio studio, and you could see the back of these speakers, and they were all developed by the BBC. And in fact, I believe you can still buy that loudspeaker, or one very much like it, which the BBC developed. Some kind of sort of standard, really, in the broadcast world. The first PC I used at school was a BBC Micro. We learnt to program on it. That was from Simon M0JQM. I'm just seeing if there's anything else. Normally I have a chance to have a look at these before the end of the speaker, but as I've been the speaker myself, I haven't been able to look at them here. G5STU says, I've got a Mint BBC B and A3000, which was the Archimedes, wasn't it? Along with a period dot matrix printer and Ethernet clock, which is the networking. The Ethernet was the name of the Acorn networking, I believe. I spent my life on the Beeb and the A3000 all through my school years. I'm now a software developer. There we are. And this was G5STU again, I think. They had 4 computer rooms, he was saying. Anyway, I really hope that this has interested you. I'm just going to check and see if there's anything else. An excellent presentation. Well, thank you very much for those comments. As I said at the beginning, honestly, I'm not an expert in these, and although I had always an interest in it, I had to look up and research most of the information that I've shared with you. So I'm pleased that you haven't given me too many difficult questions, but there is plenty out there. There's never been a better time, actually, to find out about 100 years of the BBC, with its centenary just a month or so ago from when I'm talking now. So if you do want to see any of these exhibitions that are around, looking online, I'm sure a lot of it will be there indefinitely, but some of them, like that exhibition in the Bradford, will only be on for another few weeks. So do make the most of those, because I'm sure that it's a great opportunity and great time to find out about these. Thanks for all of your feedback and your questions. I think we've covered most. Martin Ellis says, I didn't have a BBC computer, but used to envy people with them and being able to get software from the TV by sticking a sensor onto a flashing square on the screen. You know, I can remember that now. There was a little photo sensor that you put near the screen, I think, and it sent it sequentially. That was clever times, weren't they? Lovely to look back at those times. Thanks again to all of you for those comments and feedback and questions. I hope you've enjoyed it, and do have a look at some of that research. But that does conclude this webinar, and thanks once again to Studio Director Tammy Palmer M0TC sitting next to me, and the RSGB team who helped put this series together behind the scenes. We hope you've enjoyed this tonight at 8, and you'll be able to join us next time when Ben Lloyd GW4BML will join us to talk about portable operating with radio and rucksack. And if you'd like to see details of this and other webinars in the series, please visit rsgb.org/webinars, where you can also send us comments and feedback. And before I go, can I remind you about the RSGB construction competition, where you'll have all these winter evenings to complete projects before the deadline on March the 1st, 2023. Entries free for all RSGB members and will again be online this time, so you won't have to send your work away to be judged. You can find out full details by going to this special webpage, rsgb.org/construction-competition. And of course, full details will also be in forthcoming Radcoms, including features about previous winners. And finally, a tip that if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. But that's it. Until next time, this is David G7URP signing off and clear. Bye-bye.